Hi everybody, welcome to my 12th beam video. In this video I'm going to be finding what B has to be if we have all these conditions here. A load, a self-weight, and a maximum stress in this material. If you want to know something else about beams or want to see some sort of other example, feel free to check out any of my other beam videos. So if you wish to find what B is, we're going to have to use this equation here. Alright, I'm dropping the negative sign, as I will just think about it intuitively when I get there. If you want, you can keep the y in all the time and think about if it's positive or negative, but for most questions in Intro to Mechanics and Materials courses, you don't need to worry about that. You just need to think about it intuitively. So we need to find the bending moment, the distance, and the moment of inertia. The distance and the moment of inertia we can calculate just by looking at this cross section. And we'll do that last. The first and biggest thing is to find the maximum bending moment. Alright, so let's first just take a look at what the forces are that are actually acting on here. Because we have a density of the material of 10 kilonewtons per cubic meter. So let's redraw this initial problem with instead of just a density being given, we'll draw it as a weightless beam and a density as a distributed force applied along the top. Alright, so this is what we're going to replace it as. Now, what is the magnitude of this distributed force here? Well, the way I analyze a beam that has an overall, in this case, specific So when we have this sort of overall given function that so this beam, of course, is going to have an overall mass. It's also going to have an overall weight because we have gravity. Now this here, this little gamma symbol, that's specific weight. So that's basically density times gravity. So when I analyze these beams where we're given some sort of information like this, I find it most useful to give an expression that describes the overall weight of the beam. So overall mass times gravity. So we can say the overall weight, or the total weight, is equal to, let's just forget about this units that we know. It's going to be density, right? Mass per unit volume times volume. That would give us just mass. Mass times gravity is weight. Alright, now we said here, specific weight, right, is equal to rho g. So we can say the total weight is equal to, gamma times the total volume. And the volume of this beam, well, that's just going to be the length times these dimensions here. So we can write times b times 3b, alright, that's width times height times the total length of the beam. Alright, now this force here is some sort of force per length. Alright, in our case, a weight per length. Now to find that, we take the total weight and divide it by the total length. So we take this whole function and divide it by the total length. That just gives us three gamma b squared. That's a weight per length. Usually we give that q. Alright, so in this situation we're given gamma, and it's kilonewtons. So let's express it in terms of newtons. We will get All right, and Q being that. All right, so let's go and find the bending moment diagrams for each of these. Now, in this case, we're not going to know B until the very end. So it could get a little bit tricky doing your bending moment diagrams in terms of a variable. So you just got to drag that B through all your calculations. If you want, you can just take B to equal 1 for the purpose of your bending moment diagrams. Or do something else like that. Because depending on what B is, that's going to change the shape. Or just, how big are the gaps in between on your bending moment and your shear force diagrams. So if you're having trouble with that, just take B to equal 1, plot it, and then take B just to be B again later on. So an overall free body diagram, we need to find the reactions at the support. Alright, now I said the reactions are the same. That's true because P is in the middle, and when we take a distributed load that's distributed linearly like this, alright, a constant value throughout, it's going to act through the centroid of its own distribution, which is right in the middle of this green square piece, if you will, so that's right in the center of beam also. Alright, now the magnitude of the force is the force per length times length, so it's just going to be Q, which we found, L. And this force here, P, we have given it a value, 115 kilonewtons. Let's put that in terms of newtons. And taking our dimensions to be like this, we can sum up the forces in the Y to find the reaction. Alright, there we go. And now let's move into a free body diagram. But wait. Instead of explicitly going through and finding all the math for everything, alright, we're going to still do some math because we need a mathematical value to solve this equation. Let's do this free body, or not free body diagram. Let's do this bending moment diagram intuitively. Alright, so let me draw out the graphs here. Alright, so shear force. So we should actually sort of look at this beam here. So we're going to have a reaction that's going to kick us up the magnitude of the reaction. So if we start our journey on the beam, and as we progress, we're going to start at this reaction height, and then this load here, this apply load, is slowly going to push us down in a linear fashion. Alright, so we can imagine we're at a distance r above here. We push down linearly because this is a constant applied load till we get to here, and then P pushes us down. Alright, and now say it pushes us down this much, and we're still being pushed down by this load here at the same rate as we were over here. Alright, and then at the end, in order to get a zero shear force at the end, this reaction, of course, is pushing up. That's going to push us up of a magnitude R. Alright, so that's symmetric about here. Alright, it's all nice and symmetric. And the magnitude of this jump in here, like I said, is P. Alright, so let's see if we can get a bending moment diagram from this. So we know the relationship that, or we can write Alright, so if we integrate this, we'll get this. So here there's a very big positive value. So that's just going to be the slope of our bending moment diagram, alright, using this equation here. The value of V is the slope of a bending moment diagram. So here, a big positive value, we're going to have a big positive slope. Now as we go along, this positive slope is still positive, but it's decreasing in the amount that it is positive. So we're going to get something like this. Some sort of quadratic. Also, boom, it gets knocked down. Now there's no jump in the bending moment because there's no applied moment. All of a sudden we have a negative slope here. Alright, and it's not much of a negative slope, but it's going to slowly get more negative as we go. So a negative slope and then getting more negative as we go. So quadratic in the other direction. So notice this is a quadratic function for the bending moment, but it's not the same function. At this point there's a discrete jump in the slope. Alright, because if you graph the tangents at this point here, you'd see it go off like this, and a tangent from the other direction would go off like that. Alright, so a change in slope, but not a change in magnitude of the bending moment. So the maximum bending moment, as we can see, is going to be right here. Now, how did I know it was positive? Alright, I can do it just by looking at this, and we can look at the curvature of the beam. The beam is going to sag like this. Alright, now the beam is always smiling when it's bending, so we're always going to have a positive bending moment. Alright, so we need a magnitude to find our value. We need a magnitude or a numerical math, some sort of another to plug into there. So let's just take a free body diagram of this section here and get that value. I just wanted to show you this because you can arrive at the shape of bending moment diagrams pretty accurately just by intuitively looking at it. Alright, and there we have it. So just taking the sum of moments about the cut piece, doing that, allows us not to calculate the shear force. Alright, we can eliminate the shear force. So it's always a good idea to take it about the cut piece, just so you don't need to use the shear force. Because there's a chance you made a mistake and found in the shear force. You don't want that mistake to continue if you made it. Alright, so I went straight through and analyzed it. So the bending moment is maxed, like we said, at the middle, and our beam length is 12 meters, so half of that's 6. and you get this equation here. So depending on what B is, of course it's going to change our maximum value. So we need to find Y and I yet. So Y, that's just going to be half the distance of this height here. So that's going to be 3B by 2. Alright, and the moment of inertia about a centroid, BH cubed by 12. Alright, now for this equation to work, we need to find the moment of inertia about the cross-sectional centroid. In this case, the centroid is the center, makes our life easy. So the height is 3B, the width is B, so we can find I to be and I'm plugging it all back into sigma equals my over I. Alright, and we're given sigma max. So if you take sigma max, we put it in to be 10 MPa. Alright, and then we're going to have to solve for B in this situation. Alright, so what I recommend you to do, because it's quite complicated to extract B out of this, is to plot this on your computer. I like to use Desmos.com. Alright, very user-friendly site, very easy to work. And plot this as like y equals this. And then plot another line, y equals 10 MPa, alright, or 10 million. And then just find B. Alright, for our specific situation, I do that and I find B to be 0.275. Alright, which is a reasonable value. Alright, this beam is 12 meters long, alright, almost 40 feet, that's pretty long. So we have some significant loading, so you know that's a reasonable value. Alright, so hope this video helped you out, and I will see you in my next bunch of videos on beams.